Okay, so before we start today, one more announcement. Some of you would like to have, let's say, more one-to-one interaction with the TA in office hours. So a couple of office hours every week will be dedicated to this kind of one-to-one interaction, where basically if you go there and there's well, if you're the only one there, you just go and work with the TA as you normally would at the speed that you like. But if there's more than one person there, people will just have to wait. So first come, first serve. The TA works at a pace that's comfortable for the person they're working with at that time, and other people will have to wait. If you look on the announcements forum, those have been announced to everybody. So if that's what you prefer, then use those office hours, and otherwise go to any office hours. Although this week, for example, I suspect that you could go to any office hours and get one-to-one help because, well, as you've seen, the level of traffic in office hours seems to increase as the deadlines for assignments approach. So right now, you've just submitted an assignment, or at least 340 of you submitted an assignment. And the next one's not due for a little while. So this week is actually a great time to get help from TAs. And even if that means getting help with the assignment that you just submitted, getting some clarification about that. The solutions are posted, but if you are struggling to understand those or struggling to understand where you went wrong, there'll be TAs available this week, as much as any other week. Any questions before I begin? Good. All right, so we're going to spend the next couple of lectures looking at a topic that's very important in this class and actually very important in computer science in general. So in this course, we'll be looking at recursively defined functions. In some places, these are called recurrence relations. And this topic is, of course, highly related to recursion in programming languages. And it's also related to the mathematical principle of induction. And we'll see that actually for most of these kinds of problems, the way you tackle them formally is by induction. So here's an example of one of these recursively defined functions. It's a function f. It takes non-negative integer arguments and produces non-negative integer results. And I've written it down on the board in two different ways, both equivalent. So in the book, you will see definitions like this that say, what is the value of f of 0, and maybe also the value of f of 1. In this case, f with the argument 0 is 3. And if I take n, an integer n bigger than 0, so n equals 1, 2, 3, 4, 5, or so on, then it's defined as follows. You take 2 times f of n minus 1 and add 3. So if you've ever worked with recursion in programming languages, this is sort of a natural thing for you. When you write recursive functions, to avoid infinite recursion, it's important to have base cases, so something that stops the recursion where you don't make a recursive call. That's f of 0 in this case. And here's where the recursion happens. To compute f of n, I first need to compute f of n minus 1. And this is a good safe one because f of n only relies on f of k for smaller values of k. So the recursion isn't going to run off forever. The book likes to write it like this. I prefer this notation where this is a sort of standard mathematics case notations. So f of n is equal to 3 when n is 0, and it's 2 times f of n minus 1 plus 3 when n is bigger than 0. or more precisely, when n is bigger than or equal to 1. Okay. So, questions about the notation? Yeah? Greater than or equal to 1. So I want it to be defined for every non-negative integer, so this covers 0 and this covers everything bigger than 0. So if I want to write down what are the sort of the values of this thing, so when n equals 0, the value of f of n is written here, it's 3. When n equals 1, well, that says I should apply this formula. So it's 2 times f of n minus 1, so that's f of 0, plus 3, which is 2 times 3 plus 3 is equal to 9. And if I want to know what's the value of f of 2, well, that's 2 times f of 1 plus 3. F of 1 we know is 9, so that's 2 times 9 plus 3 is 18 plus 3, so that's 21. And we'll do one more. F of 3 is 2 times f of 2 plus 3. That's 2 times 21 plus 3. This is 42 plus 3 is 45. So this thing is defined, f of n is defined for every non-negative integer n by this formula. Okay? So very often we end up with these kinds of recursive definitions because they just sort of fall out from whatever problem we're studying. We'll see that. Sometimes they fall out if you're programming because you've figured out a way to solve a problem recursively, and somehow you get a function like this which describes the running time of the thing that you're, the running time of your program. Just as often when you're trying to count something, somehow the most natural way to figure out the size of a set involves, we'll see a few examples of that, involves creating one of these things. And while this is perfectly fine and valid and it completely defines the function, this doesn't really, we can't look at this and immediately get a feeling for what the function looks like. Is it growing fast? Is it growing slow? We could write a program that computes these values to see how fast it's growing for the first 20 values or something. But this doesn't give a nice summary of the function. So very often what we want to do with these recursively defined functions is to solve them. And that means to find some other expression for these things, so an expression for f of n that doesn't look like a recursion like this, but just looks like a formula that we're used to. So if you look at this one for a while, you'll see a few f of 4 here is 93. And maybe if you have good imagination, you might now make a guess at what the value of f of n is. So guess at some formula for the general value of f of n. And if you're really creative, maybe you would guess that f of n is equal to 3 times 2 to the n plus 1 minus 3. Why not? And so you're going to guess that that's the case for all integers n bigger than or equal to 0. So that's my guess. We can try it out. For example, if I look at 3 times 2 to the 0 plus 1 minus 3, what's that? That's 3 times 2 is 6 minus 3 is equal to 3, and that actually is equal to f of 0. We can try it for n equals 1, 3 times 2 to the 1 plus 1 minus 3. This is 3 times 4 is 12 minus 3 is 9. And look at that. That is equal to f of 1. We figured that out, that that's correct. And we'll try it for one more. If we take n equals 2, so this is 3 times 2 to the 2 plus 1 minus 3. This is 3 times 8 is 24 minus 3 is 21. And indeed, that equals f of 2. So the evidence suggests that our guess is correct, at least for the first 3 values. Now, that's not a proof, because you can cook up examples where your guess is correct for the first 20 values, but it's wrong for the 21st. So no amount of checking like this is going to be enough. How do we verify formally that it's correct for every value of n? Yeah. So we're going to use proof by induction. And so remember, proof by induction is basically the counterpart to recursion. In a proof by induction, you first establish that the thing you're trying to prove, in this case, this is the thing we're trying to prove, that it's true for some small case or some small cases. In our case, the only thing that we need to check is that it's actually true when n equals 0. And then you assume that it's true for all of the values smaller than n, and use it to prove it for f of n. Okay. So let's do this. So we don't even need these things. They were helpful as a test. So the proof of this is by induction on n. And the base case, n equals 0, we've done it here. We evaluate this formula with n equals 0. We get the answer 3, and we check that that agrees with the definition of f of n, and it does. So that's handled. So now, assume that f of k is equal to 3 times 2 to the k plus 1 minus 3 for all k smaller than n. So it's true for k equals 1, true for k equals 2, true for k equals 3, for everything except, or everything leading up to n. And now we want to prove it for n. So the strategy is always the same. You have a recursive definition of f of n, so you use it. 2 times f of n minus 1 plus 3. And so this is true by definition. Now, f of n minus 1 is f of k for k equals n minus 1. So this thing here, our assumption, called our inductive hypothesis, tells us what the value of that thing is. So let's substitute that in. We get 2 times what's supposed to go in there is 3 times 2 to the n minus 1 plus 1, which is n minus 3 plus 3. Okay. So just take f of n minus 1 and apply the inductive hypothesis. That's safe to do because we've assumed that it's true for anything smaller than n, and n minus 1 is smaller than n. All right, so 2 times 3 times 2 to the n, that's 3 times 2 to the n plus 1. 2 times minus 3 is minus 6. And then let's not forget the plus 3. And we're left with 3 times 2 to the n plus 1 minus 3. So f of n is equal to 3 times 2 to the n plus 1 minus 3. And indeed, that's the thing we were trying to prove. So this funny little function here has a cleaner description. A formula like this, 3 times 2 to the n plus 1 minus 3. By looking at that, we can see a little bit more than we get by looking at this. Very roughly, yeah, the big thing here is this 2 to the n plus 1. That's growing exponentially with n. It's multiplied by 3. Subtracting 3 doesn't actually make that much of a difference when we're talking about big values of n here. Okay. Yeah?
For this one, where does n plus 1 come from? Like, I get where the 6 comes from, but where does the n plus 1?
So the n plus 1 is just our guess at what the answer was based on, I don't know, examining this sequence. So how someone came up with that guess, probably through trial and error. Maybe they tried some other guesses that looked right. But ultimately, the n plus 1 just comes from the fact that it is, it's the answer. So any questions about that? Yeah. Where? Here? Okay, because f of n minus 1 is equal to, let's write it really, we're applying the inductive hypothesis. So the inductive hypothesis says f of k is 3 times 2 to the k plus 1 minus 3 for all smaller values of k. So that says it's 3 times 2 to the n minus 1 plus 1 minus 3. And of course, n minus 1 plus 1 is just n. Yep. Yeah, I would say you're plugging in n minus 1 as k into this formula, not to confuse things too much.
What did that say up there? 3 times 2 to the power of n minus 1 plus 1. Just to illustrate where the n minus 1 is the thing that's in here, the argument to f. Yeah. So we'll do lots of, I will do some and you will do lots of these sorts of things. So it's good that you stop and ask me questions now. Yeah.
So you're proving true for n minus 1, not just n, right?
I'm proving true. This is the proof that it's true for n, using the assumption that it's true for everything smaller than n, but in fact, the only thing we really need it to be true for is for n minus 1. So this is the proof that f of n is equal to 3 times 2 to the n plus 1 minus 3. And some, you may, depending on where you learned discrete math from, some people like to make a big deal about whether you need to assume that it's true for n minus 1 or whether it's true for all the values smaller than n. That's a sort of a silly distinction to make. It's always somehow, you can always do it this way. Assume that it's true for all the values of k that are smaller than n. So I don't distinguish between strong induction and weak induction, and whatever you want to call it. All right. Good. So let's take a look at another couple of examples of functions that you can define this way, just so that I don't get them wrong. Here's a function g of n, which is equal to 1 if n equals 0, and it's equal to n times g of n minus 1 if n is bigger than or equal to 1. Does anybody recognize this function? Yeah. It's the factorial function, right? G of 0 is equal to 1. G of 1 is equal to 1 times g of 0, which is 1. G of 2 is equal to 2 times g of 1, which is 1. G of 3 is equal to 3 times g of 2, so that means that it's 3 times 2 times 1, and so on. Times g of 3. So this, more concisely, is the factorial function, defined recursively like this. Another one. You can define functions of more than one variable recursively. So you say it's 1 if k equals 0 and n is bigger than or equal to 0. It's also equal to 1 if k is equal to n and both of them are bigger than or equal to 0. Otherwise, it's b of n minus 1 k plus b of n minus 1 k minus 1 if n is bigger than or equal to 1 and k is in 1 up to n minus 1. Does anybody recognize that one? Yeah. No. Not Fibonacci numbers. Does this formula look familiar? B of nk equals b of n minus 1k plus b of n minus 1 k minus 1.
Pascal?
Yeah.
This is Pascal's identity for the binomial coefficients, right? Usually the Pascal one has n plus 1 here and n's in here, but that's just a change of notation. But you know, the number of ways to choose k element subset from an n element set. I take one of my n elements and make it special, and either I choose k elements that don't include the special one, or I choose the special one and k minus 1 other elements. So this is Pascal's identity for binomial coefficients. And then if we look at these two things, this says if k is 0 and n is bigger than or equal to 0. So remember, n choose 0 is 1. There's only one way to choose an empty set from an n element set, and it's the empty set. And this is when k equals n, that's also the number of n element subsets of an n element set. There's only one of them. It's the whole subset itself. And then Pascal's identity covers all the other values of k. So this thing is a sort of complicated recursive definition of n choose k, but actually not so complicated. When you draw Pascal's triangle, this is what you're doing. You're drawing it one row at a time, and you're just making sure that when I want to draw row n, I have all the stuff that I need from row n minus 1 in order to draw it. So lots of things you can define recursively this way. Now I will just use a slightly different, more compact notation for the next one, because it's one that we'll be using a lot. So I'll write it as f subscript n. And it's a three-case one. 0, if n equals 0, 1, if n equals 1, and otherwise it's f of n minus 1 plus f of n minus 2. So that's if n is bigger than or equal to 2. So that one we can write out. So let's put n here, f of n here, n is 0, f of n is 0, n is 1, f of n is 1. And from this point onwards, the next value of f of n is obtained by adding together the previous two values, right? So for 2, I take f of 1 plus f of 0. That gives me 1. For 3, I take f of 2 plus f of 1. 4, 5, 6, 7, I get 5 plus 8 is 13, and 8, I get 21. So, does anybody recognize these numbers? Yep. Fibonacci numbers. So these are the famous Fibonacci numbers discovered by, Fibonacci, whose first name, these actually follow the the usual rule of naming conventions, which is these kinds of things are never named after the first person to discover them. I guess they're named after Fibonacci because somehow Fibonacci had a nice story about rabbits reproducing that led naturally to this kind of recurrence. I don't even remember it. It's certainly not biologically accurate anyway. But this was supposed to be after n generations of rabbits. Not sure how these first two generations reproduce when it's 1 rabbit and 0 rabbits, but whatever. The nth Fibonacci number was going to be the number of rabbits you should have after that many generations. So this is a famous sequence, and the real characterization here is f of n is f of n minus 1 plus f of n minus 2. Now, we can ask, is there, like the previous example, is there a formula for f of n that doesn't involve recursion like this? What do you think the answer is? Yes or no? Maybe no. Maybe yes. Sometimes the answer is no. I mean, sometimes you can make recurrences that don't have short definitions or short solutions that can be described in terms of the usual sort of mathematical operators that we have. But in this case, the following theorem is true about Fibonacci numbers. We have two magic numbers. This one is called phi. This one is called psi. And I'm going to write something that's superfluous, but we'll end up using later. So there's two magic numbers. This one, does anybody know what it's called? The golden ratio. It's this beautiful ratio. It's about 1.618 something. Shows up, for instance, in Da Vinci's paintings. In fact, Da Vinci's sort of perfect man is all golden ratios everywhere among these things. So that's called phi. And then it has an ugly little brother who's not the golden ratio. This is a negative number minus the fractional part of this. Not pretty at all, but it's there. And what's special about these two numbers? Where do they come from? Well, they're the solutions to this equation. If I put phi here, this is true. If I set x equal to phi, this is true. And if I set x equal to psi, this is also true. This is a quadratic equation. So typically those have two solutions. And these are the two solutions for this particular quadratic equation. All right. Then, for all n bigger than or equal to 0, the nth Fibonacci number is phi to the power n minus psi to the power n divided by the square root of phi. And unless you've seen this before, this is shocking. I mean, look at the Fibonacci sequence here. I mean, what's the most obvious thing about these Fibonacci numbers? They're all integers. And of course they're all integers because they start with 2 integers at the bottom here, and then you just add other ones together, so you just get more integers. Look at these things. This is an irrational number. Its decimal expansion goes on forever. This is also an irrational number. Its decimal expansion goes on forever. Problem is root 5 is irrational, so its decimal expansion goes on forever. And how do we get the nth Fibonacci number? We take this thing and we raise it to the power of n. We subtract this thing to the power of n, divide by square root of 5, and we get exactly the nth Fibonacci number, an integer. So that seems almost unbelievable. Would you like to see a proof now or later? Now. Okay. So, we'll start down here. Proof by induction. By induction on n. Okay, so first thing to notice is this recurrence here. The general term, so the one that we're really concerned about is the nth term when n is big. It depends on 2 smaller values of n. So that means, for example, at some point we'll be trying to prove the inductive hypothesis. So we'll be trying to prove that f of n is equal to that thing over there. And we'll need to assume that it's true for 2 smaller values of n. So if you think about that, that means that the first time we can start to do that, to start to use the inductive hypothesis, is when n is bigger than or equal to 2. For values of n smaller than that, we can't rely on the inductive hypothesis. And that means we actually need to check 2 base cases. We need to check the case n equals 0 and the case n equals 1, because n equals 1 is not defined in terms of smaller things, so we'll need to check that as well. So this has to have 2 base cases, and the reason it has to have 2 base cases is that these 2 things depend on, f of n depends on n minus 1 and n minus 2, so in particular f of 2 depends on 1 and 0. Yeah?
Do we need to check for n equal to 2 as well?
We don't need to check for n equals 2. For that we can apply the inductive hypothesis. Okay. All right, so let's check. Okay, try for n equals 0. We get phi to the 0 minus psi to the 0 divided by the square root of 5. Well, anything to the power 0 is 1. So phi to the 0 is 1. Psi to the 0 is 1. Divide that by square root of 5. That's equal to 0. And that's f of 0. So the base case n equals 0 checks out. Now we need to check n equals 1. Phi to the 1 minus psi to the 1 divided by the square root of 5. That one is more annoying. So let's write it out. 1 plus the square root of 5 divided by 2 minus 1 minus the square root of 5 divided by, all divided by 2, all over the square root of 5. So let's see what we've got. We've got 1/2 minus 1/2. So those disappear. We have root 5 divided by 2 plus root 5 divided by 2, right? This is negated, but this is also negated, so that's positive. So root 5 divided by 2 plus root 5 divided by 2. That's just root 5. And the whole thing is divided by root 5. And it is indeed equal to 1. So the two base cases, well, and 1 is the value of f of 1 by definition. So the two base cases check out. So now we do just what we did before. We want to prove that it's true for, all right, so base cases are done. Now assume f sub k is equal to phi to the k minus psi to the k over root 5 for all k in 0 up to n minus 1. And now for n bigger than or equal to 2, we want to prove that it's true for f of n. So we apply this formula, or the definition. So this is f of n minus 1 plus f of n minus 2. Now, this is f of k for a value of k that's smaller than n. This is f of k for a value of k that's smaller than n. And we're assuming that what we wanted to, I mean, we know what those evaluate to. That's our assumption here. So let's write that down carefully. This first one should be phi to the n minus 1 minus psi to the n minus 1 divided by the square root of 5. That's what the inductive hypothesis tells us. The second one should be phi to the n minus 2 minus psi to the n minus 2 divided by the square root of 5. Let's tidy that up a little bit. We've got some phi's. They're both positive. So we've got a phi to the n minus 1 plus a phi to the n minus 2. And we've got a psi and a psi, both negative. And everything is divided by the square root of 5. So nothing special there. So here we have this little thing with a lot of psi's in it, or a lot of phi's in it, rather. Let's take out the common factor. So what's the common factor between these two things? Phi to the power, well, this one has phi to the n minus 1. This one has phi to the n minus 2. So n minus 2 is smaller. So that thing is really just phi to the n minus 2. To get back this term, I need to multiply by phi. To get back this term, I only need to add 1. All right, so you see that part? That's these two things. Take out the common factor, which is phi to the n minus 2. You get this. And you can do the same thing with these two, right? So that's minus psi to the n minus 2. We have 1 psi. And a 1. And let's not forget that we're dividing everything by the square root of 5. All right. Does anybody see what we should do next? Every piece of information that you need is written on the board. There was one piece of information I gave you that seemed to be unimportant at the time,
but now it's actually important. Phi plus 1. Is that equal to something else? Yep. Phi is a solution to this equation. So phi plus 1 is phi squared. So this thing here is phi squared. And this thing here, the ugly little brother, that's also a solution to this equation. So it's psi squared. But now we're done, right? Phi to the n minus 2 times phi squared, that's just phi to the n. Psi to the n minus 2 times psi squared, psi to the n divided by root 5. That's what we were trying to prove. So this is mind-blowing, first time you see it, because there's no way that this thing looks like it's going to give you integers for every value of n, but it does. And the underlying reason, or one of the underlying reasons, is, of course, it's here. It shows up in the proof. That's where these two magic numbers come from. They're the solution to this thing. And then everything nicely cancels out. Okay. So, a couple of notes about this. Phi is approximately 1.618034. And psi is approximately minus 0.618034. Okay. This decimal expansion, the exact decimal expansion goes on forever, but these are close estimates. So this thing then, so this number here, the absolute value of psi, right, it shows up in the solution, and right, we take psi to the n. It's a negative number, so when n is even, that gives us a positive thing, but when n is odd, it gives us a negative thing. So it's somehow flip-flopping between positive and negative as n is getting bigger, or as n increases. But, so the absolute value is less than 1, which means that as n increases, it actually tends towards 0, right? Think of this as a half, and then a quarter, and then an eighth, and then 16th. I mean, this goes very quickly towards 0. So this expression here is phi to the n minus something that's going quickly towards 0. In fact, it's always, this second part is always less than 1. So if you want a really cheap sort of estimate to the Fibonacci number, I mean, just take phi to the n divided by square root 5. The difference between that and the true Fibonacci number, well, it's less than 1, and actually it tends to 0. So the two tend to be exactly, I mean, getting closer and closer as n gets bigger and bigger. So really, the right way to think about how quickly do these Fibonacci numbers grow? Well, I mean, this captures almost everything. You're off by a little bit if you only consider this first piece. The second piece is becoming less and less important as n gets bigger. So the moral is the nth Fibonacci number is about 1.618034 to the power n. And that's good to know because Fibonacci numbers show up a lot, including in the running time of certain algorithms, which we'll see an example of next class. But they also show up in sort of counting problems, which we'll cover shortly. But let's see how these things can be, how recurrences in general can be applied to counting problems. So let's take Sn is equal to the set of n-bit binary strings with no 0, 0. So, for example, S0, all the 0-bit binary strings that don't have a 0, 0 inside them, well, there's only one length 0 binary string. It's the empty string, and it doesn't have a 0, 0 inside it, so that's what that is. S1, well, there are two binary strings of length 1. One of them is 0, and the other one is 1. And neither of them contain a 0, 0 inside them. But things get interesting with S2 because there are 4 2-bit binary strings, but I'm not allowed to include 0, 0 because it has a 0, 0 substring inside it. And if I just want to do one more example, S3. There are 8 binary strings of length 3. I'll write them all out and then we'll cross out the ones that we can't have. Let's see. So which ones are we not allowed to have? This one has 0, 0 in it. This one also has 0, 0 in it. This one has a 0, 0 in it. And the rest are okay. So let's define Bn to be the size of Sn. Let's try and figure out how many strings there are in this set Sn. How many strings of length n that don't have a 0, 0 in them. And as you may guess, we'll somehow get a recursive function that defines Bn. And we already know the base cases. B0 is equal to 1. B1 is equal to 2. B2 is equal to 3, and B3 is equal to 5. So now, assume that I'm considering start this way for n bigger than or equal to 2. So now I'm interested in Sn for n bigger than or equal to 2. So I'd like to somehow describe what the strings in Sn look like in terms of strings in Sn minus 1 and Sn minus 2, or maybe Sn minus 3, or smaller things.
So if I look at a string in Sn, it has n bits in it. So look at the first bit here. Maybe it's a 1. So if the first bit is a 1, what kinds of strings can I put here? So in total, I need to create a string that doesn't have any zeros in it. So what am I allowed, or not any zeros, that doesn't have 2 zeros in a row in it. So what am I allowed to put in here? Yep. Yeah. So this thing here, I can fill in with any element of Sn minus 1. A binary string of length n minus 1 that doesn't have 2 zeros in a row. If I take one of those strings that doesn't have 2 zeros in a row, and I tack a 1 onto the front, that doesn't change the fact that it doesn't have 2 zeros in a row. So that's perfectly good. On the other hand, I can't put in any string here that has 2 zeros in a row because I'll get back a longer string that has 2 zeros in a row, which I don't want. Okay. So any string in Sn either starts with 1 and is followed by a string in Sn minus 1, or, well, what if it doesn't start with a 1? If it doesn't start with a 1, and it's a binary string, what can you tell me about it? Starts with a 0. It's a binary string. Everything is either a 1 or a 0, so I've already somehow dealt with the case where the string starts with a 1. Let's see if it starts with a 0. What can you tell me about it now? Yep. Yeah. So it can't be, so if it starts with a 0, the second thing can't be a 0 because we're not allowed to have 2 zeros in a row. Well, if the second thing can't be a 0, then it has to be a 1. And then I have n minus 2 other things to fill in here, which I can fill in with anything as long as it doesn't contain 0, 0. Which means here I can put in any element of Sn minus 2. So either starts with a 1, exclusive or starts with a 0, 1, followed by a string in Sn minus 2. Okay, so if Bn is the size of Sn, then that says that Bn is equal to the number of strings of length n that start with of these strings that start with a 1, plus the number of these strings that start with a 0, 1. So the number of these strings that start with a 1, well, that's just the number of things in Sn minus 1, which is Bn minus 1. And the number of things that start with a 0, 1 is just how many ways we can fill in these n minus 2 other bits. and that's Bn minus 2. So we get a recurrence, and that's it, right? The thing starts with a 1, or it starts with a 0, 1. There's no other possibilities. Anything that starts with a 1 is covered here. Anything that starts with a 0 is covered here because it can't start with a 0, 0. So now we have this general recurrence. This holds for n bigger than or equal to 2. And so if we want to write it down carefully, we get Bn is equal to 1. If n equals 0, it is equal to 2. If n equals 1, and otherwise it's equal to Bn minus 1 plus Bn minus 2 if n is bigger than or equal to 2. Does this look familiar?
Fibonacci.
I mean, this part here, this looks like the Fibonacci sequence. Bn is equal to Bn minus 1 plus Bn minus 2. That's the Fibonacci recurrence, right? F of n is equal to F of n minus 1 plus F of n minus 2. The only difference is the n equals 0 and n equals 1 cases are a little bit different. But if we look at the Fibonacci sequence, so we've got what was it? F of 0 is equal to 0. F of 1 is equal to 1. F of 2 is equal to 1. F of 3 is equal to 2. F of 4 is equal to 3. F of 5 is equal to 5. F of 6 is equal to 8. Here in our sequence, this is B0, this is B1. So this is B0, this is B1, therefore this is B2. It's B1 plus B0. And this is B3, and this is B4. And so we see the general pattern now, which is that Bn is equal to F of n plus 2. So, that gives us our result. And Bn, remember, that's the number of n-bit strings that don't contain 0, 0. Somehow, this set of strings, the size of it is, I mean, it's almost the Fibonacci numbers, it's just off by 2. Which means that, again, we now have right, Bn is the size of a set, so that's an integer thing. And by that result on the Fibonacci numbers, the size of that set is given exactly by this insane formula of, now it's going to be B is just the name for the size of the set. Right. Bn is just the size of the set Sn. Yeah. So the size of the set of 0-length strings that don't contain 0, 0 is equal to 1, which also happens to be equal to the Fibonacci number 2. Yeah, so the size of this set is again equal to this strange thing that has irrational numbers in it raised to integer powers, which happens to be an integer anytime you use an integer power. All right. Let's, okay, questions there? Yep.
What's the side of
N plus 2, yeah. So, questions there? Let's do something similar and see where that takes us. So the main takeaway there is we were trying to define basically the size of a set of strings, and the trick was to, so strings of length n, the trick was to somehow take a nibble out of the problem and say, just look at the way those strings start. See if you can figure out a few little cases that cover all the different ways those strings can start, and then they're followed by a string of the same form but shorter. So that's a sort of general strategy you can use for these string problems. You know, if I ask you for binary strings that don't contain some particular value, you work that way. Look at how they start and see what you can do there. And that also works for non-binary strings. So let's say Sn is equal to the set of length n strings over the alphabet A, B, C. So for example, S0, how many strings of, oh, not all of them, that don't contain AA. This is similar to what we did for binary strings, right? Binary strings, we had 2 letters in our alphabet, and we asked for not having any double zero. So this looks similar. Should be able to attack it the same way. So S0 is sort of trivial. It's only the empty string. S1, well, I can have the string of length 1, which is just A, or the string of length 1, which is just B, or the string of length 1, which is just C. And S2, though, well, there's lots of things in there. They can be AB, AC, BA, BB, BC, CA, CB, CC. The only one of the 9 strings which is missing is the double A. And I won't do S3 because you know, there's 27 strings of length 3 here, and only a handful of them are have the double A in them, so it won't bother. Okay. So let Bn equal to the size of Sn as before. So we know B0 is 1 and B1 is 3. That's all we'll need to know. And now we want to look at what happens for n bigger than or equal to 2. So we'll do the same thing. We're considering a string of length n It's over this 3-letter alphabet, and it's not supposed to contain any AA. So look at the first letter here. So if that first letter is a B, what can I put here? Yeah, any string of length n minus 1 that doesn't contain an AA. So any element of Sn minus 1. So in here, anything from Sn minus 1. In fact, that's also true if I put a C here, right? Put a C here, then I can also put anything in Sn minus 1. Okay. So either starts with B or C followed by an element of Sn minus 1. All right. So what's the other option? If it doesn't start with a B or a C, what does it start with? If it doesn't start with a B or a C, it starts with an A. And if it starts with an A, what can you tell me about this letter? It has to be a B or a C. And then the rest of it is a string of length n minus 2 that doesn't contain a double A in it. Okay. Or starts with AB or AC followed by a string in of Sn minus 2. And actually, that's all that can happen, right? Starts with a B or a C, or it starts with an AB or an AC. Can't start with an AA, so that covers all the cases. So if we write that down as a recurrence, that means for n bigger than 2, B of n is 2 choices for the first character, followed by B of n minus 1 choices for the remaining n minus 1 characters. Or 2 choices for the first 2 characters, it's either AB or AC, followed by B of n minus 2 options for the remaining n minus 2 characters. And so this recurrence, the definition of Bn, needs to have a definition for Bn minus 1 and a definition for Bn minus 2, which means we need base cases for B0 and B1. All right. And you can make some wild guesses as to what this thing resolves to. Maybe I'll show you if I have time, but there's something else I want to do first. But this does have a solution that has exponents in it and weird things similar to Fibonacci. So this is not the Fibonacci recurrence, right? There is a B of n minus 1 and a B of n minus 2, but each one of those is multiplied by 2. And that makes a big difference. But what I would like to look at before that is what happens if I change this question just a little bit. So this says, I look at all the strings over this 3-letter alphabet of length n, and I insist that they should not start with an AA. So the pattern that I'm not allowed to have is AA. What if I just change that pattern a little bit and say, what if I want to avoid an AB instead of an AA? Should that change the answer? There's a specific two-letter pattern. Yeah?
I have a question. Where does the multiply by 2 come from?
Multiplied by 2 because we can put an A, a C, or a B here, followed by this other thing. So we have 2 choices for the first letter instead of just 1, unlike the previous example. And similarly here, we have 2 choices for those first 2 characters. It can be B or C in the first case, or it can be AB, AC in the second case. Okay, so the answer should be the same, right? If we think the answer is the same, we have the proof written on the board here, so let's try and follow it and see if it still makes sense. Yeah, okay, S0 is this, so, right, that part is still fine. This has to change a little bit, because we're not allowed to have AB, but we are allowed to have AA, so that part's pretty much the same. This part I don't know yet, we need to look over here. For n bigger than or equal to 2, a string in Sn either starts with a C, B, followed by something in Sn minus 1. Okay, so if I put a C or a B here, then yeah, as long as I put something here that doesn't have an AB in it, I'll get something that doesn't have an AB. So that part seems to check out. So far so good. All we got to do is check this one. So if I put an A here, what can you tell me about this next character? It's what? It's A or C. Okay, so if it's AC, then yeah, it's AC, and then I put anything here that doesn't have an AB in it, and I'm fine. But what if it's AA? If it's AA, then it's not the case that I can put anything that I want here. Because here I might have the string right? BCCCCCCCC, that's definitely in Sn minus 2, but when I tack AA onto the front of it, I get an AB showing up here. So something's changed. But this doesn't look right. It's not just, it can be AC followed by a string in S of n minus 2, but it can't be an AA followed by something in S of n minus 2. So what is it? In fact, really what do these strings look like if they don't have an AB in them? So maybe they start with a C or a B, or they start with a bunch of A's. So all A's for a while, and then finally, maybe they hit a C. Okay. And once that happens, I can get a string here, but if this was of length k, then this is a string in Sn minus k. And if I do this carefully, I'll see that I get a recurrence that looks like this. So this part stays the same. That's what happens if you start with a C or a B. Or maybe your string is all A's. That one's allowed. Or maybe your string is n minus 1 A's followed by a C. Or maybe it's n minus 2 a's followed by a c, followed by a string of length 1, or n minus 3 a's followed by a c, followed by a string of length 2, and so on. So you end up with a very different answer, and that's not what we expected to happen, right? This looks like a very different recurrence from replacing this with 2 times b of n minus 2. Small change in the question, which looks like it shouldn't have changed anything, actually changed the answer completely, which is an indication that you have to be careful in dealing with these kinds of things. So I recommend, I know you're probably not interested in doing this right now because you just did an assignment, but you are now in the best possible state for starting assignment 2. Assignment 2 has a whole section on pigeonhole principle, which we did last class. It has a whole section on recurrences, which we're starting to do now, and you know how to solve some of these already. So this is really the best time to start. You're equipped better than you will ever be.